Hi, welcome to another video. So I've been looking at this PEAVEY CS3000, so 3000 watt amplifier that's 1500 watts into 2 or 4 ohms RMS per channel, so 1500 watts times 2, 3000. But you can actually bridge this and get it to become a mono amp. I'm assuming it's still up at 3000 watts into one speaker. First of all, these heatsinks sit on each side. This was as dusty as hell under the cover. These heatsinks sit here and here, and there's a heatsink compound. So I guess the clever design is they've used the collectors for the, I think they're Toshiba transistors, I forget, but all the collectors, so plus the positive signal and the negative signal, the collectors, the case can sit on here. Yeah, this becomes the actual speaker output. And fluctuates your positive and negative around 0, so no insulators required. Just stick all the transistors on the board upside down and clamp this down. There's 2 more heat sinks down here, one over the other side. I think, is that an insulator? It looks like there is an insulator on there. Yeah, there's a mica washer on here. Now these are difficult to test with a transistor tester or even a meter on diode test, because these are insulated gates, bipolar transistors, so you can't get a reading really between the gate and the emitter. But so I took them out and put them on my bench power supply, stuck a supply via resistor onto the collector, then ground, and then supplied 5-6 volts on the insulated gate, and they both turned on. So I'm not sure, I think in the normal running mode you get something like plus or minus 60 from this huge supply. No doubt this is a good power supply, shouldn't ever go wrong. So you get plus or minus 60, which is positive 60, minus 60, and they call that the plus and minus low rail. Then, switched in later, or depending if it's bridged or not, you get plus and minus 120, so plus 120, minus 120, and these insulated gate bipolar transistors are used to switch in those supplies. Well, so this is a similar design to the Dynacord systems, except you haven't got a million covers and switches on top. You've got a lid, but instead of having lots of screws to hold down the circuit board, they've used a clever idea. There's these little lugs scattered all over the place, and you get 3 screws. I think there's one there, one inside here, one down the front here, one over the other side on the left, and you simply slide the whole board. Don't know if you can see that on the camera. There's one of the lugs. So you simply undo the 3 screws, slide the whole board up, and lift it off and away from these lugs. I've been on this amplifier for days, not diagnosing the fault, but looking at the circuit drawing, which is freely available from PEAVEY, and I've been deciding whether to even tackle this amp. As I said in a previous video on the Mackies, if you don't understand how they work, you haven't got a hope in hell of trying to repair it, not without blanket bombing it. These power transistors are only a few pound each, but if you had to change all of them, so I think this is like the negative half side, positive half side, might be back to front, same over the other side, over there. Because all these transistors are strung in sort of parallel to deliver huge amounts of current, all these high power resistors, I think 0.33 ohms, are in line with the emitters. And that's a basic amplifier. That's the right channel. Obviously that's the left power supply, so that's easy enough to work out. I had a protection light on the front that PEAVEY call, don't know if you can see it down there, DDT, and it's a trademark, so I forget what DDT stands for, but it's apparently an enhanced way. It measures if the amplifier is clipping and protects the amp or protects the speakers, and possibly if there's a fault with the amplifier and it's going to stick out DC onto your speaker, which you won't want, presumably that would come on to tell you it's in full protection as well. So you've got a power light that actively tells you, presumably, when these rails, high power rails have turned on. I'm not sure, I haven't looked at that power LED with reference to these transistors that turn on the supplies. But as I was saying, so I spent hours looking at the circuit board once I took off the heat sinks. Thought, well, if you got one channel working, at least you can do a comparison. Yeah, that's easy enough if you don't understand the circuit drawing. But I had a look at these LEDs. If I turn it on, I'll show you what the fault is. So you saw the power, you had a couple of relays click, and the power comes on later, and then this DDT, that one goes out, and this one stays on. So that's obviously 1 amp. What's this bit down here? Yeah, is this the audio input? But then at the back on this backboard for selecting bridged or normal stereo, you've got 2 chips down there. Then you've got a board down the front with the LEDs on. You think, well, what is this part? What's that part? What are these big resistors? What's that circuit down there? And I was thinking, should I have even offered to have a look? So for example, this coil outputs the power of this side of the amplifier direct to the speaker, and that coil sort of matches the impedance with the speaker and delivers the correct power into an inductive load via this and a high value resistor at the back. So that center line, as I say, is 0 volts but rises positive and negative reference to 0. Let me turn this amp off. This line here goes out to the speakers via these relays. So even though this protection light was on, I tested a little diode down here, and there was power out of this diode, which meant that relay was turned on, which means there's power out to the speakers. Someone said this channel was dead. I haven't actually tested it because the light was on. So we had power out to the speaker, so no DC out via the protection light. So I think, right, it must be part of the clip circuit. But I'm looking at the circuit drawing, and you've got the amp for one channel, then another part of the drawing is the amp for the other channel, then another part of the circuit drawing is the protection, and then they keep on referring to, so clip left, clip right, plus 24 control, which I'm assuming is the power on the front for each side. But then it's pre-zob, and you think, what the bloody hell is pre-zob? Well, I've sussed out pre-zob is actually measuring the voltage here before the relay. So have you got any DC voltage before the relay cuts in and isolates your speakers? So that where the hell has pre-zob come from? So you might be familiar with amplifiers, but if you don't understand the term pre-zob, how can you fix something? Well, I'm not going to do a screen capture just for this little bit, but this is in PEAVEY's circuit drawing. So it's a PEAVEY CS3000, as I say, and it's very similar to the 4000 watt amp as well. But you've got the clip right. If I scroll down a touch, OTA left. Is it out left on the A channel? So it's OTA. What the hell is that? Maybe it's out. Connects to the output channel. So then the clip, then the control right, then this pre-zob. What the bloody hell? What's pre-zob? Even now I know it's the output from the amplifier before the relay. What's zob? But so it's before the relay, so hence the pre. Maybe zob, that's an abbreviation in some foreign language, God knows. Anyway, that's signal right, control right, so power, minus 18, 24 volts, and we had a light on. So I looked at the front LED, you need power out to the LED to turn it on. So I looked at that, simple. Fortunately I had these for the Mackies. I ordered some of these, I think, from eBay, and it came like 10 transistors. Or 10 sorts of transistors. In fact, I'll pull it up now. Maybe have a look on eBay if you plan on fixing one of these PEAVEYs. Those 10 transistors are comprised of these. So 5551, which this PEAVEY uses, 5401, this PEAVEY. Then down the bottom, other random transistors. the Mackie uses 3904, 3906. I'm not sure if this PEAVEY uses these two, but the Mackie uses these two at least. And that was something like £1 or £2 for 10 of each of these transistors. So I thought, great. I tested these transistors in the circuit and they tested okay. But I thought, I have had faulty transistors where they'll turn partly on even though they shouldn't. They won't like die and go short circuit. They can become intermittent. It's rare, but it happens. So even though I put my meter on diode test, get half a volt between the base, half a volt between the base and emitter, and between the base and collector. That's normal, and it's not short circuit between the collector and emitter. I thought they can be faulty, so I thought, oh, for the sake of 5 minutes, I'd replace that. Even though I measured the voltage, 26 volts here, I had less than 26. So on a PNP, having less than the emitter here means it's going to turn on slightly. But so I had 26 here, 25 and a half here. I actually get sort of 24, 25 volts out. It turns sort of hard on. And then this resistor here, or sorry, this transistor here. So you know you need half a volt above the emitter for it to turn on. So I had something like minus 17 and a half here, minus 17 and a half here, so that shouldn't have turned on. So this won't turn on, which means it's not going to pull current this way down to the minus 18, which means that base should sit up at the supply. The way it's wired up here should sit up at the supply, not be slightly lower than the emitter. So on, yeah, there's a little arrow, current flows that way on a PNP, and you've got to take power away from the base to turn it on, and NPN put power onto the base higher than the emitter for that to turn on in this example. So I changed that, but when I took them out, the light went out, so I thought, well, at least I'm on the right track somewhere around here. As I say, they tested okay with the meter, but yeah, it costs you 5-10 minutes to swap them over if you got them. The light remained on, so I thought that only leaves this capacitor. Now it's rare, or rare for sort of over 0.1 microfarad, but this is meant to be polarized, but looking at the cap on the board it's not. I thought that maybe if this is going short circuit, that is pulling power off of this space by a small amount and turning on the light. Bearing in mind we haven't got the protection relay in. The relay's on, so it's normal, so is it just a faulty light circuit? And so I thought, well, I'll take this out and see what happens. Right, so I'm looking at this C200. Oh, this one here. I actually took it out, but I'll put it back in to demonstrate. So you saw that light was on. So what I'll do, put my heat gun on there for a couple of minutes and then take it out with these tweezers. And there we have that 1 microfarad meant to be polarized capacitor. So I'll stick it on there next to that transistor I pulled out. There's the other one, which happened to be okay, but yeah, these are pennies, and you know, you can spend ages thinking it's okay and it can be intermittent, take my word for it. And just like capacitors, yes, they don't generally go wrong, but they can. So now I've taken that out, and the theory is it's starting to go short circuit, and it's pulling the voltage down to this minus 18, so pulling it down to ground, pulling power off of this base, which will, because it's a PNP, taking power away will turn this on. Turning this on will get power out to the LED. Incidentally, I didn't unplug it. That's how this felt like a big trip switch, and it is. It's a massive mains trip. Don't know if it's isolating the live or the neutral. Probably looks like the live with the brown on it. But you know, with that turned off, we're isolated with a proper isolating transformer. So yeah, just work away with it turned off. But I guess for safety, when you're working on your amp, unplug it from the mains. But I don't listen to my instructions. Anyway, let's turn this on. So watch, I think you'll see the signal lights pop up for a nanosecond as you hold this on there. So we've got DDT, DDT, power cuts in, so that's presumably those isolated or insulated gate bipolar transistors. And now look, DDT lights out, DDT light out, but that was out anyway. But it's doing the test, so some voltage comes from somewhere. Maybe that's, we've got a 1 microfarad capacitor, so it takes time for that to discharge or charge up and knock these lights out. But so turn that off again. Back on. Both on. And both off. So we should be good to go. Right, you can see I put the heat sinks back on. Clean their transistors, plenty of heatsink compound, because those transistors, they're all forward biased, and even though maybe they're passing a few milliamps, it's, I don't know, maybe up to 200 volts across the rails, they actually start to get warm within seconds of turning them on. The hotter they get, the more current they'll pass, which means the hotter they'll get, with the voltage drops further, and you get thermal runaway, and they will heat themselves up and blow up. So, but the heat sinks on stop destroying the transistors. That's not one thing I haven't looked into on these amps. I saw various bridges over here. Can you actually bridge the high rails, the plus or minus 120? Can you stop those turning on so that you can test the circuits in situ without the heat sinks? Because these heat sinks cover everything up. That's a bit of a downside to testing these. As I say, if you're turning it on and those transistors are okay, don't leave it on for more than sort of 10-20 seconds. Touch the transistors, you'll feel they're getting hot. Anyway, so I'm turned on, no DDT lights, got the volume set halfway on this 40 channel, and as with all my previous amplifier tests, I'm going to use my analog device's signal generator, giving me a sine wave, but it's very low output, sort of less than half a volt, and what I've established, these PEAVEY amplifiers, unlike the Mackeys that will give you full power at 44 millivolts, these sort of want at least 1 volt input to give you any decent amount of power. Anyway, let me turn my microcontroller on to give me my sine wave. There's a signal. We're up at half volume, and using a speedcon connector on the back of the amp, I've wired it to an 8 ohm 100 watt resistor, and this actually does get quite hot. So I've got it balancing on a, where is it, Benidorm ashtray. So that's the output of this right hand channel, and that's the frequency sweeping up. So you can see we're at 800 Hertz at the moment. We're on 11.5 volts peak to peak. If I turn my microcontroller off, you'll see the bottom end response is very good. Let's bring that in a bit. Works in 100 Hertz, 130, 40, 50, 60. I've actually got this going quick. Now I did some tests last night. I run this PEAVEY amplifier from 30 Hertz, and I've kept on going to see where is the 3D point. Well, yeah, where does the power drop off to half, or the power at the output. And most amplifiers, they used to quote 20 Hertz to 20 kilohertz plus 3 dB, and then over the years with the invention of better op amps, better transistors, better biasing techniques, you go 20 Hertz to 20 kilohertz, 0.5 dB. Now 1 dB is that amplitude, or the output power, times by nearly 0.8. So 1 dB variation is very good, but modern amps have a deviation of half a dB or less. Now this PEAVEY amplifier, this very one on this bench, this started dropping off at over 150 kilohertz. Couldn't believe the frequency response on it. So if I expand that out, you'll see we've still got a nice clear sine wave. So if I turn the volume up a touch, Right, so that is actually this amplifier up at full volume with only sort of less than half a volt peak to peak going in. So the input amplification isn't as sensitive as like one of the Mackies, but then this amp can drive, 100 different speakers, whereas the Mackie is just designed to drive its speaker. And you can see we're up at 2.5 kilohertz, and that amplitude will not change not till it gets over 100 kilohertz. So the quality of these amps are bloody good. But I have to say, so these PEAVEYs, or certainly this CS3000, it's certainly a powerful amplifier, certainly well constructed, frequency response is second to none, no distortion, no noise, no nothing, absolutely a very good amp. But with the heatsinks the way they are, difficult to test without removing the heatsinks. Once you remove the heatsinks, everything starts getting hot and you can only leave it on for a short while, so don't know if there's a way of stopping the rails turning on. And just that little circuit for the DDT light, there's probably nothing wrong with this amplifier, it was just the DDT light circuit that was faulty, not the amplifier itself. Not sure how old this amplifier is, not sure if there's anything on this transformer. So this had failed because of one surface mount capacitor. So it begs the question, is that just a one-off, or with age can we expect more capacitors to fail? And if that's the case, you then got to look at the resale value on these. Or are you going to buy one that's sort of 5, 6, 7 years old, knowing capacitors can fail randomly? Other than that, very good design, but boy does it take a while working out what part of the circuit does what and how is one part interconnected with the other. And I could go on, but definitely good quality amplifier. So looking back at the scope, we're now at 6.3 kilohertz. It's flat, 20 hertz to a good 150 kilohertz. That noise coming through is just the communication with my signal generator. I'm telling it to, increase in frequency. So again, like the other amps I've repaired, I can't answer individual questions on what may be wrong with your amplifier, because these are sophisticated and complex, and it took me hours to establish how this DDT light function works, and took me a while to find out one leaky capacitor. So normally resistors blow up, transistors can go short circuit or open circuit, and in this case it was a capacitor. So if you come along and say you've got no power rail, is it the IGBTs, insulated gate bipolar transistors, or have you got a smaller driver transistor that's faulty, or is it a cap? It could be absolutely anything, as I found out on this one yesterday. Hopefully this has helped. Thank you very much.